Hello everyone and welcome to today's webinar about the climate load generator in advanced design. My name is Evelina Pelkanoglu. I am solution specialist in Climatic for advanced design. I am also a structural civil engineer. I hold a PhD in computational mechanics and I have worked as a structural civil engineer in a consultancy in the past. Today we will see how to use the climate generator in advanced design in order to create and calculate the climate loads such as wind and snow quickly, effectively and efficiently. So the agenda for today is the climate load generator for wind and snow. First of all, I would like to introduce the term load areas that is going to be used by me a lot during this session. The load areas is a set of artificial elements that they are used for the correct application and distribution of wind loads on the structural elements of the structure. They are not structural elements, meaning that they do not provide any stiffness or act as diaphragms. This is the default option. The user obviously can change that, but generally the load areas are artificial. It's basically a way of the generator to identify the shape of the building and apply the loads accordingly. The climate load generator in advanced design can deal with range of different geometries of the buildings. For example, the most frequent ones, the rectangular structures with different types of roofs, such as flat roofs, monopitch roofs, duopitch roofs, and hipped roofs. The climate load generator can deal with buildings with horizontal setbacks, with or without parapets. Vertical walls can be used as well and can be identified by the climate load generator, and the wind load variation can be calculated on those structures as well. Multi-span roofs with or without parapets. Outer panels can be calculated as well using the climate load generator, and the wind load specifically can be identified on them, and also wind loads and snow loads on awnings and protruding roofs. Finally, climate loads can be assessed in canopy roofs, either monopitch or duopitch canopies, and of course wind load can be calculated for lattice structures, such as this one, for example, in a scaffolding element. First, I am going to present the climate generator for wind, and then we will have a demonstration of how to use the climate load generator in advanced design, and then I am going to present the climate load generator for the snow. In this particular example, the building is rectangular. There is a flat roof on this building, and these information are given for this particular structure. So there is in region A in the interactive map for wind in the UK means is on this green area. The height of the building is 3 meters, the terrain category is 2, and there is no significant orography. By selecting the region, the fundamental value of basic wind velocity is selected. This comes directly from this map according to the Eurocode and the British Annex, and the basic wind velocity is also calculated according to the Eurocode. The terrain category that is in this case is category 2 can be used in order to identify those parameters in the Eurocode from this particular table, and all those parameters are used in order to calculate the mean wind velocity. There are other parameters, the parameters C0 and CR. The first one is for orography and the second one for the roughness. So basically those two parameters take into consideration the properties of the terrain around the structure. And also there is the turbulence factor and the turbulence intensity. So basically, in order to calculate the wind load, turbulence is also considered on the equations. All these parameters are defined precisely in the Eurocode 1 for wind loads. Using all those parameters, the basic velocity pressure is calculated, and using all those parameters and the basic velocity pressure, the peak velocity pressure is identified, and this is basically the value, the pressure that is needed, that is going to be used later on with the coefficient of external and internal pressure in order to define the wind loads in all the vertical structural elements of the structure as well as on the roof. All these procedures in order to calculate all those parameters is described clearly on the Eurocode. The first element that is going to be checked is the vertical walls, and the case that is going to be investigated is the wind load that blows along the X direction. According to the Eurocode, as you can see on this figure, the following areas, the following zones, to use this term, are identified. So if the wind blows along the X direction, the first phase that the wind meets is the zone D is developed. The opposite surface of D is E, and the areas that they are vertical to D and E have the zones A, B, and C, depending on the value of this parameter E. So, according to the Eurocode, the parameters B, H, and D are also defined. So, B is the length of the area that the wind is perpendicular to. D is the length of the area that the wind is parallel to, and E is defined as the minimum value between B or 2 times H. H is the height of the wall, as you can see here. So after defining those zones and the fraction H to D, the coefficient of external pressure can be found on this table for all these different zones. However, there is also the internal pressure and the coefficient of the internal pressure, the CPI coefficient. According to the Eurocode, normally this there is an equation in the Eurocode to calculate this coefficient. However, because this coefficient is affected by the openings and the percentage of openings and how big the openings or how small the openings are in the walls, the Eurocode suggests to use either a positive CPI of 0.2 and a negative CPI of minus 0.3. So basically, for each wall, for its wind case, and for its wall, the following combinations of loads are created. The positive CPI with the CPEs that they are identified on this table, and the negative CPI with the CPEs that they have been identified earlier. So for one load case of wind, we have two different combinations in order to take into consideration both CPIs. Moving forward now to the flat roof, again the Eurocode identifies 4 different zones, as you can see here, and gives the CPI and CPE for each of those zones. Again, the parameters B, H, and D are defined, and there is a particular table where you can find the values of CPE for its zone. Again, the different values of CPI needs to take into consideration, which means that again different combinations have been created in order to take into consideration these two values of CPI. One observation here is, as you can see, for zone I, there are 2 different values of CPE, which means that 4 different combinations need to be created. For example, I'm going through this one first. Assuming a positive CPI means that the CPE is going to be, for zone I, needs to be 0.2 first and minus 0.2, which leads to 2 combinations here. And again, in order to consider both values of CPI, is going to create 2 different combinations for a negative CPI. Combining now the external and internal coefficients multiplied by the peak wind velocity pressure we already calculated, the wind loads for positive and negative CPI have been generated in all the areas of the structure. And now we will going to see how to use the climate generator in advanced design, because the procedure to follow in order to calculate the wind loads in Eurocode is quite tiring and obviously time consuming, and sometimes the shape of the structure is not very straightforward, so an engineer could or might find that is not very straightforward how to decide on all the values of these different parameters depending on the description of the Eurocode. Now we will see how we can use the climate load generator in advanced design and simulate the wind loads for this structure we were investigating on the slides before. So first of all, we will see that the load areas have been introduced to this structure. These are the green and the blue areas in the structure, that they cover the structure all around in order the software, the generator, to identify the shape of the structure and apply the wind loads accordingly. Second, the wind load case family needs to be created. This can be done here by selecting new and create the load case family. You create the wind load case family in order to define all those information we saw earlier. and allow for the software to calculate all those parameters for you. So by clicking on the left hand side of the wind load case family, we have all those information the software needs in order to calculate the parameters for roughness, turbulence intensity, orography, and basically needs all those information in order to calculate the peak wind velocity. So when you click on this icon here, you select the area you are in the UK. I'm going to select here around Southampton, which is basically the lowest, 22 meters per second wind speed. And obviously by selecting that, changing if I need to, in our case I'm not going to change anything, but changing the height of the building or the altitude allows for the software to take into consideration all those information and calculate all those parameters in order to find the peak velocity pressure that is used later on from the generator in order to calculate the wind loads. And then on this feature in the ribbon of the software, you can select the climate loads generator, and this generates the wind loads for this particular structure. Here is the wind along the X direction, is the case we investigated earlier. I am going to make the load areas transparent in order to be able to see the wind load on the different areas of the structure, and I'm going to see the first one. So as long as the wind blows along this direction, obviously this is going to be the zone D, and these areas of the wall, the ones that they are parallel to the direction of the wind, are going to have the regions A, B and C we saw earlier. So this first one is going to be A, and here is the CPE for region A, minus 1.2, and as you can see here, CPI says 0. We saw earlier that the Eurocode suggests that for CPI, the coefficient of internal pressure, we should get values of 0.2 and minus 0.3. The British Annex for the CPI suggests that sometimes 0.2 is quite conservative, and as long as there is the consideration of minus 0.3 of the negative internal pressure, by having a positive internal pressure basically makes the results more conservative, so suggests the CPI of 0. So as we will see here when we go through all those combinations in a few minutes, we will see that for the British Annex, basically the software identifies 3 CPI. So does the procedure for CPI 0, CPI 0.2 and CPI minus 0.3, and these can be seen in different combinations, such as, so when S is used, S2 plus S used is CPI 0, minus S corresponds to CPI 0.2, and D corresponds to CPI minus 0.3. All these plus S with different numbers here take into consideration what we saw earlier for the roof, where we have different cases for the CP on the roof, and for flat roof sometimes these combinations might be identical, but for different type of roofs you need all 4 of those. So a general rule is that minus S corresponds to CPI 0.2, minus D corresponds to CPI minus 0.3, and plus S corresponds to CPI 0, especially for the British Annex. And then we are moving forward to different wind direction. For example, the Y wind, which blows along that direction, and all the combinations have been created using the load generator in seconds, as you can see. By clicking here, I am enabling all the loads on the structure for this particular wind load and for this particular CPI, V0. And if I'm zooming here, you can see the regions on the roof as well. And basically all the structure has been identified from the generator, the shape of the structure has been identified, and the load has been applied accordingly. And of course, in order to create the combinations for the analysis and design later on, by clicking on combinations and allow for simplified combinations, as you can see here, the combinations have been generated. We can, for example, selecting the 103, where the live loads have the coefficient 1.35, 1.50 for the live loads, and the case 3, which is the wind load along the X direction, when the CPI is 0, is basically the first one we investigated, is the secondary one, and comes with coefficient of 0.9. And if I'm scrolling down slightly, here is a different combination where again the wind is a secondary load, but with 0.6 coefficient, when the dead and live have a coefficient of 1. So all the different combinations, and again all the different combinations have been identified from the software, from the generator, and the wind has been taken into consideration with all the different ways that can be combined with the other loads on the structure. I would also like to show you a different type of structure. In this case, we have a dual pitch roof with a flat roof as well, and I'm going to generate the wind here as well. I am going to generate the wind creating a load case family again, the wind one, and I am going to select again a different area. Probably I am going up to the north in order to get a wind speed that is higher compared to the previous one, and then by selecting the generator, as you can see here, I get the wind load in all the areas of the structure. I am going to hide all the load cases of the wind, and I will generate just one. So the wind now blows along the X direction, so this should be the region D. Region A, B and C will be generated on those areas, and E is going to be that area. And if I zoom in, you will see here the first region to be A with a CPE of -1.2, as we saw earlier on the Eurocode. Again, all the different combinations have been created. We can see the wind load on the roof as well. In this case, the regions on the roof are slightly different, because if I zoom in, you can see that we have a region F, just because it's a dual pitch roof, and in dual pitch roofs there is a region F according to the Eurocode. So depending on the shape of the roof and obviously the geometry, the regions will be probably different, and the software has the option to identify all those different parameters and create the load area, the wind load and the the wind loads accordingly. Moving forward, we are going to see how to deal with snow load now. The same structure is going to be investigated again, a rectangular base with a flat roof. We are going to go through the process the Eurocode suggests for snow load, and then we will see how we can use the climate loads generator that is building in advanced design in order to accelerate the whole process and calculate the snow loads more efficiently and quickly. The Eurocode suggests to identify first the region and the altitude of the area that the structure is located. Again, there is the same map. This is for the characteristic value of snow load on the ground in different regions. We're in region 2 again. For this particular case, this area changes slightly from wind to snow. So we were in region 1 for wind, we are in region 2 for snow, if you are located around here in Southampton. So for this particular case, we're in region 2, which means the characteristic value of snow load is 0.6. If the altitude changes, the Eurocode suggests to change this value using certain coefficients, and then these three coefficients are used in order to be multiplied by the characteristic value of snow load on the ground and identify the total snow load on the roof. The first one takes into consideration the shape of the roof, if it is monopitch, duopitch, flat. The second one is the exposure coefficient and basically combines any and takes into consideration any influence of the wind load in the area and how certain parameters and certain phenomena in the area affect the snowfall and the snow, the development of the snow in the area. And the final one, the CT, is the thermal coefficient and is associated basically with heat transfer and how easily or difficult the snow might melt in a roof. And for example, in a glass roof, the snow might melt easily and quickly compared to a roof that is not made of glass. So this thermal coefficient needs to be taken into consideration. Most of the time is has a default value of 1. So using those coefficients, the final wind load is calculated and is either increased or decreased depending on the properties of the roof of the structure. And then after we have identified the snow load according to the Eurocode, we can go back to advanced design and see how we can use the climate load generator in order to generate some snow load for this structure. Now we will see how to use the climate load generator to create the snow load in this particular structure. Again, you can see the load areas be introduced on this structure. And as I mentioned earlier, for the snow load, it's very important to have the load areas on the top of the structure to have created the shape of the roof we have in order the generator to identify this type of roof and apply the snow. Again, we create the load case that corresponds to snow, and then by clicking on the snow load case family, we have to identify and apply all those information we saw earlier in order the software to identify the area the structure is in order to calculate all those parameters we saw earlier. By clicking on this icon here, again the interactive map of UK is showing on the screen, and you select the area you would like to be. Again, I'm selecting an area here in Southampton, so it's region 2, and as you can see, the snow load is calculated, the exceptional snow load is calculated as well. We have this option in advanced design to allow for exceptional snowfall or exceptional snowfall accumulation. In this case, I have disabled those two options, but if I enable those, you will see when I run the generator that you will get loads that correspond to this situation as well, if you think that this situation needs to be considered in this case. And also we have the exposure factor and thermal factor here that the user can change them if they want to. We also have the altitude. The user can define the altitude according to their thinking, or can probably leave the default parameters. Again, running the climate load generator, and enabling the snow. I need to make the load areas transparent. And as you can see here, this is the snow load on this flat roof. By clicking here, you will see the value is -0.5. Also check this type of structure we checked earlier, the one with the 2-pitch roof. I can run the snow generator again. I am going to select again an area here around Southampton and run the calculator again. This is the altitude now is 0. And as you can see here, we can see the roof on the snow on the roof again, and the different values of the snow, obviously due to the difference in the altitude, and the snow is obviously affected from the different parameters we set up during the calculation. Another important thing before closing this demonstration for today, particularly for the wind load, when set up the wind load for a structure, you have the option to select if there is an opening on a load area, and this can be done by selecting the load areas on the walls. So if you would like to take into consideration any opening, by selecting the load area, for example this wall here, and on the properties on the right hand side you have the option to select if there is any opening, if the face is completely open, if there is an opening, what is the area of the opening, or what is the percentage of this opening. So in order to get this information considered, Advanced Design has this option for you to select this on the properties area, and when they run the generator will take into consideration the fact that you had an opening on this particular wall. After finishing with the snow load in Advanced Design, this session is about to end. Thank you very much for your attention, and I'm happy to take any questions.